I'm Laura Centeno. In this video, I'm going to explain to you the parallel RLC circuit. The name or the letters in the name are because of the components, which are a resistor, an inductor, and a capacitor. I'm going to review some equations, some loads, and the dynamics of the system with a step function input.
Here we have a diagram for the parallel RLC circuit. As we can see, there's a resistor, an inductor, and a capacitor. Then we have to do the general balance in the circuit. We gotta analyze the currents entering and the currents leaving the node. We have the current in the total system, which is IS, minus the current in the resistor, which is IR, minus the current in the inductor, which is IL, minus the current in the capacitor, which is IC. This all equals 0. Now we have to rewrite the currents in terms that we actually know. The current in the resistor equals the voltage over the resistance. The current in the inductor equals 1 over the inductance times the integral of the voltage in time, and the current in the capacitor equals the capacitance times the change of voltage in time. Then we are going to rewrite the equation. In order to simplify the calculations, we gotta rewrite this equation again, but in terms of derivatives. As we can see, it is a second-order equation. What we did in here is to divide all over C in order to disappear this capacitance. We take a look to the equation, we can see that it is pretty similar to the RLC series circuit equation. Our next big question is, how do I calculate the current in the system represented as IS? The answer is vectors. As each brand of the circuit has a phase angle, it cannot be combined in a simple way. We cannot say IR plus IL plus IC is the current in the system. Then we know that the total current will be the sum but of the vectors. I am drawing in here the graphic representation of the vectors. As we can see, IC and IR can be summed up in order to simplify the calculations of the total system current vector. As we know, we can solve the vector calculations with the Pythagoras theorem, not method. Then we have that the current in the total system squared equals the current in the resistor squared plus the difference between the current in the inductor and the current in the capacitor squared. I forgot to say that the system has a certain frequency, which is represented with this F. The impedances are the effective resistance of an electric circuit to alternating current. This is the general formula for our circuit. The impedance of the inductor can be described with this formula. So can the impedance of the capacitor. But what does this weird W, which is actually an omega, means? It equals 2 pi the frequency, and this is usually called resonance frequency. Another property of the system is the reactance. It can be defined as the opposition to the passage of the alternating current. It is usually represented with an X, and these two are the formulas of the reactance of the inductor and the capacitor. The units of the reactance are ohms also. We can rewrite the impedance in terms of reactance and a resistor, and doing some algebra we will get into this equation. This will be also related to the vectors solution that we reviewed before. Now we're going to review some of the signals that we can get. There are 3 different cases. Case number 1. 2 different real roots. Alpha 1 and alpha 2 are different, and the set is higher than 0. This is also called overdamped. Case number 2. There are 2 equal real roots. Alpha 1 and alpha 2 are equal, and the set equals 0. This case is called critically damped. Finally, we have the case 3. There are 2 complex roots. Alpha 1 and alpha 2 are added up to an imaginary part. The set is below 0 and it is called underdamped. Here we have the graphic representation of the signals. As we can see, underdamped have some oscillations. This is because the decrease in resistance leads to oscillations. Finally, we can analyze the inductor current. As we can see, there is like a peak. In the underdamped case, we can calculate the overshoot at this point.